Hi, I'm Mark Barsamian. In this video, I'll be introducing the concept of optimization, and I will then do examples that are optimization problems of a particular type. They will be single variable max-min problems about revenue and profit. This material from section 4.6, optimization. More specifically, it's actually material from near the end of that section, pages 307 to 311, examples 3, 4, 6, and 7. The corresponding homework is this collection of 3 exercises from section 4.6. Before starting the new material, let's recall some stuff from previous sections that is going to come up. The definition of critical numbers for a function. Remember that a critical number for a function is an x value that has 2 properties. It's an x value where f prime equals 0 or f prime does not exist, and it's an x value where f of x does exist. We had the definition of absolute extrema from section 4.5. Those were introduced in the video for homework 61. An absolute max for a function is a y value with the property that it is the greatest y value on the domain of the function. That is, if you compare f of c to f of x for all x in the domain of the function, f of c is greater than or equal to f of x. An absolute min is a y value f of c with the property that it's less than or equal to f of x for all x in the domain of f of x. And recall these theorems about absolute extrema from section 4.5. We discussed these in the video for homework 62. The extreme value theorem says if the function f is continuous in the domain as a closed interval, then that function will have both an absolute max and an absolute min on that interval. And then a more general theorem, theorem 2, called locating absolute extrema. It's about where absolute extrema occur. Absolute extrema, if they exist, must occur at critical numbers or at endpoints of the domain. Theorems 1 and 2 are the basis for this procedure called the closed interval method for finding the absolute extrema on a closed interval for a function that is continuous on an interval. And this procedure was discussed in the video for homework 62. It was this 5-step procedure involving making a list of important x values, the critical numbers for the function, and the x values that are the endpoints of the interval. And those are the only places where absolute max or mins can occur, and we're guaranteed that there will be an absolute max and there will be an absolute min. So the idea of this procedure is you make this list of these important x values, and you just make corresponding list of the y values, and you identify the greatest y value on that list and identify that as the absolute max. And you find the least y value on that list, and you identify that as the absolute min. Now, of more interest to us today will be the situation where the domain of the function is not a closed interval. Now remember that in that situation, we're not guaranteed that there will be any absolute maxes or absolute mins. In the video for homework 63, we found that a couple of approaches that would work in situations like this. For some familiar function types, the approach can be this. First, consider the end behavior of the function to determine which kinds of absolute extrema will occur. And then find the locations of those extrema in the following way. Find the critical numbers of the function that are in the domain and compute the values of f of x at those critical numbers and at the endpoints, if there are any endpoints. And then identify the absolute max or min that you know will occur. The key thing is you start by figuring out which kind of absolute extrema will occur, and then you make this list of y values, and you look at that list for the greatest or least y values that you are expecting to occur as the max or the min. For functions that are not familiar function types, we can't figure out just by thinking about the end behavior what the behavior of the graph is going to be, so we can't argue about which kinds of extrema we expect to occur or not occur. So for problems like that, we took this approach. We started by finding the critical numbers of the function in the domain, and then determine if any of those critical numbers is the location of an absolute extremum by either studying the sign behavior of f prime to determine the increasing decreasing behavior of f of x, or using the second derivative test, studying f double prime and using the second derivative test for absolute extrema on an interval. That's this test. The idea is if you have a place on the graph where the first derivative equals 0, so the graph has a horizontal tangent line, and if you know that the second derivative is greater than 0, as in the graph is concave up at that point, and that's the only critical number on your interval, then you can say that that x value is the location of an absolute min for the function on that interval. In this current section, we're starting material from section 4.6, optimization. Optimization refers to problems that are simply absolute max-min problems, but they may have complications. Here's a list of some of the complications you may encounter. The problems may be presented as word problems about applications to real-world situations. You may have to figure out a mathematical model. That could be an equation. The initial mathematical model may involve more than one variable. If it does, then you'll have to figure out how to extract from that mathematical model a function of one variable. And the domain might not be a closed interval. Remember, when finding absolute maxes and mins, the easiest situation was the situation where we have a continuous function on a closed interval. Things get more complicated, less predictable in situations where the domain is not a closed interval. So that's the idea of optimization problems. In the current video, we'll be discussing the content from Homework 64, single variable optimization problems about maximizing revenue and profit. So single variable means that you don't have to deal with that possible complication. Maximizing, so again, optimization problems are max-min problems. And the ones that we're going to discuss today are about maximizing functions that are revenue functions or profit functions. Example 1 is similar to 4.6, number 19. A company manufactures and sells X cameras per week. The weekly price-demand equation is this. So remember that X, the number of items that are manufactured and sold, is called the demand. And remember that price refers to this small letter p, the variable p, and it's the selling price per item. So question A is to find the price function, graph it, and determine its domain. So remember, price function means we want to solve this equation for p in terms of x. So there's the price function. Now I've just solved the equation for p in terms of x. Now since we're thinking of it as a function, we should use function notation. Now we still have to graph it and determine its domain. We'll do that on the next page. How do we graph that? It might help to realize that the form is this. So the form is a line equation. So we have a line that has a y-intercept at the point 0, 300 and has slope minus 1 over 30. So there's a graph of this abstract equation. Now, the point, though, is that this graph of an abstract equation is not the same as the graph of the price function. Why? What's the difference? Well, in the price function situation, x represents the number of items manufactured and sold. You can't sell a negative number of items. So we have to have x greater than or equal to 0. So there's the idea that x has to be greater than or equal to 0. But Also, you can't sell items for a negative price, so we have to have price greater than or equal to 0 as well. So there's the graph of the price function. It is not the entire green line. The green line is the graph of the abstract equation, y equals negative 1 over 30 times x plus 300. So we need to find the domain of this function. So that means we're going to need to find the coordinate of this point, the x-intercept. So we see that the x-coordinate of that point over there, that's the x-intercept, is x equals 9,000. So the domain of our function is x has to be greater than or equal to 0 and less than 9,000. So that's the end of question A. Question A, again, was to find the price function, graph it, and find its domain. And you realize that finding the domain makes a lot more sense when you look at the graph of the function. And think about, again, the key distinction between the graph of an abstract mathematical equation, that's this line that goes on forever, versus the graph of a price function on a restricted domain. The same formula for those two things, but one has a restricted domain and one does not. Let's go on. Question B is, if the goal is to maximize the weekly revenue, what price should the company charge for the cameras, and how many cameras should be produced per week? Well, there's a lot to digest there, but the thing to think about first is this, weekly revenue. To do anything here, we need to come up with the revenue function. So the revenue is the number of items sold times the selling price per item. In other words, it's the amount of money that you bring in from selling the items. Well, the number of items sold is the demand. The selling price per item is the price. Those are denoted by little x and little p. So we have this equation that says capital R, the revenue, is little x times little p. Notice that's an equation involving capital R, little x, and little p. But from the previous part A, we have this formula for p. It's actually a function of x. So p of x is 300 minus x over 30. So in other words, if I replace the letter p with the price function, p of x, then the right side is just a bunch of stuff involving x, and so that amounts to a function of x. So that's the revenue function. So there's the revenue function. Now, we should note again the distinction. This is a mathematical expression that normally we would think of as a function with domain all real numbers. It's just a polynomial. Written that way, it's probably clear that it's a polynomial. If that were an abstract polynomial, its domain would be all real numbers. But the domain is not all real numbers because this function came from putting together this price function, which had a certain domain, and this letter x, which is required to be greater than or equal to 0. So the result is that the domain of the revenue function is the same as the domain of the price function that was used to build the revenue function. The price function has this domain, and so if I use that price function to build something else, the thing that I build is also going to have that same domain. So there is our revenue function. Now let's go back up and read the question. The question says, if the goal is to maximize the weekly revenue, what price should the company charge for the cameras, and how many cameras should be produced per week? Well, let's think about the larger picture. We're trying to find the situation that maximizes revenue, and we're supposed to say what price and what quantity, what number of cameras sold will give that maximum revenue. Well, we should think about the quantity first because we have revenue written as a function of demand, as a function of X. So we should take this given question, which asked first about price, and we should answer it in a different order from the way it's written. So in other words, we should ask this question: what value of X maximizes the revenue? Find that value of X. That'll be the number of cameras that should be produced each week. Once we find that value of X, then we'll write the corresponding value of P. So let's write our strategy here. So our strategy is find the value of X that maximizes R of X, and then find the corresponding value of P. So we have an absolute max problem. So we'll resume this on the next page. So there's our problem now. We have to maximize that function on this domain from 0 to 9,000. Notice this is now an abstract mathematical problem. We just have a max problem. So what's our strategy? Notice this is a continuous function on a closed interval, and so we can use the closed interval method. Let's review what the closed interval method says. We're going to find the critical numbers in that interval, and then we're going to make a list of the important X values, the endpoints of the interval, and the critical numbers, and we're going to evaluate the function. We're going to find the values of the revenue at all those important X values. And we're looking for the absolute max, and we'll just find the greatest Y value on that list. So there's R prime. Now let's find the critical numbers. That means X values that cause R prime to be 0 or R prime to not exist. Well, R prime is a polynomial. So R prime always exists. There are no X values that cause R prime to be undefined. So there's our only critical number. And notice that that is in our interval. So now we make a list of the important X values and the corresponding values of revenue. We'll do that on the next page. Now here we're going to make a list of the values of revenue. Now we can use whatever form we want for the revenue. There's the standard form of the revenue, but remember when finding Y values or function values, it's often easier to use the factored form of a function. Here's a factored form of revenue that will actually be more useful. So X times the quantity 300 minus X over 30. All right, let's compute the values. So there is our list of corresponding revenue values, and we see right away that the absolute max is this value. It occurs when X equals 4,500. So we see that to maximize the weekly revenue, the company should sell 4,500 cameras per week. Now let's go back up to the question. How many cameras should the company produce each week? Okay, we've answered that, 4,500. But the other part of the question is, what price should the company charge? Well, we have to find the corresponding price. The price is given by that formula. So once we know the value of X, we use that formula to compute the price. So we get a value that P equals 150. So in other words, the company should sell the cameras for $150 a piece. Now before going on, let's go back up and look at the price function. On this graph of the price function, notice that when X is 4,500, the value of the price is 150. So there's a point on this graph whose coordinates are 4,500, 150. Now look at this function. What is it telling us? It tells us that if the price is higher, for instance here, price is high, the value of little p is high, and the value of little x is low. So in other words, when the price is high, not many cameras will be sold. On the other hand, at this end of the graph, the price is low. The value of p is very small, but the value of x is large. So when the selling price is low, a lot of cameras will sell. Notice that when P is 300, X is 0. If the selling price is $300, nobody will buy a camera. On the other hand, if the cameras are given away, that is, if the price is 0, 9,000 people per week will come and get their free cameras. Now notice what that tells us in terms of revenue. This situation, when X equals 0, that corresponds to the price of the cameras being $300, and nobody bought a camera, so that's why there's no revenue. Now think about this situation. That's when X is 9,000. That means the price was 0. 9,000 people per week come and get their free camera, but they're being given away, so the revenue is 0. Let's go on. Question C is, what is the maximum possible weekly revenue? Oh, well, we've already figured that out. We found this. The revenue when X is 4,500 is $675,000 per week. All right, let's go on. Question D. If the goal is to maximize the weekly profit, what price should the company charge for the cameras, and how many cameras should be produced per week? Now, what's up with this? Let's go back up and look at the beginning of the problem. We had that given price-demand equation. We also were given a cost equation. We haven't used that, but that's going to come up because remember that profit is revenue minus cost. So we will use this cost function to build the revenue function. I think I just misspoke. We'll use the cost equation, the cost function, to build the profit function. We've already built the revenue function. So there's our profit function. So our goal is to find the value of x that maximizes profit on that same domain. Let's start by finding the critical numbers for x. So there's our critical number for the profit function. Now remember what we did before. When we were finding the value of x that maximized revenue, we made this list of x values and y values. Now, there's a fair bit of work in computing these y values, and I didn't even show it all. I didn't show the work that went into producing this y value. It's arithmetic. It's not rocket science, but it's tedious. But let's think about something. Here we can be clever. We should have been able to be clever the previous one as well. Notice that our profit function is a parabola facing down. So it will have a high point that is the location of the point where there is a horizontal tangent line will be the highest point on the profit function graph. So the place where there is a horizontal tangent line, that is the place where p prime equals 0, is going to be the location of a max. We don't have to figure out, we don't have to make the list of all the important x values. That is the endpoints are to the left and right of this x value. So the endpoints on that graph are going to have lower values of p of x than x equals 40, 50. So x equals 40, 50 is the location of the max. So the company should sell 4,050 cameras per week. Now remember the rest of our question. The question was, how many cameras should be produced per week? Okay, we've answered that, it's 4,050. But the other question is, what price should the company charge? Well, we need to find the corresponding value of price. We'll do that calculation on the next page. To maximize weekly profit, the company should charge $165 per camera, and they'll sell 4,050 cameras per week. So notice, they should raise the price per camera. They'll sell fewer cameras, but apparently that's the way to maximize profit. Question E is, what is the maximum possible weekly profit? Well, that just means we're going to find the value of capital P of x when x equals 40/50. So the result is the maximum possible weekly profit is this value, $456,750. Let's go on. Question F says to illustrate the results from B, C, D, and E on this graph of revenue and profit. Now, which is which? Well, notice that revenue, remember we knew that the revenue was 0 when x was equal to 0. So this must be the revenue function because that's the one that goes through the origin, 0, 0. So that's why I chose red. Red is for revenue. And the other graph is profit. I chose purple for profit. Now notice a couple more things. Remember that we noticed that the revenue would be 0 when x was 0 and would also be 0 when x was 9,000. When x was 0, that meant that no cameras were sold, so the revenue was 0. So the point 0, 0 is on the revenue graph. And when x was 9,000, that was because the price was 0. So 9,000, 0 is on the revenue graph. Now, what about the max? That's what we're supposed to illustrate. We found that when 4,500 cameras per week are made at a price of $150 per camera, that the revenue will be maximized. So that means that the max on this graph has these coordinates. When 4,500 cameras are made each week at a selling price of $150 per camera, the revenue is $675,000. Now, what we found in question D was that to maximize profit, you should raise the price, sell fewer cameras. So the maximum in the profit graph occurs a little bit to the left. Notice the weekly profits, in addition to having a peak a little bit to the left, the weekly profits are lower than the weekly revenue. That makes sense because profit is revenue minus cost. Also notice a couple of things. Remember, you can't sell a negative number of items, so X can't be negative, and you won't sell things for a negative price. You won't pay people to come and take your items away. So revenue is always greater than or equal to 0. But you can lose money. In this portion of the graph, the value of the profit is negative. That means that the costs exceed the revenue. Also over here, there's a place in the profit graph that's below the axis there as well. So profits can be negative. The company can lose money. Well, that's the end of that example. Let's go on. Example 2. This one's similar to 4.6, number 25. A coffee shop sells 1,600 cups of coffee per day when the selling price is $2.40 per cup. Question is, what is the daily revenue? So the solution is that the revenue is $3,840 per day. Question B. A market survey predicts that for every 5-cent price reduction, 50 more cups of coffee will be sold per day. So the question is, how much should the coffee shop charge per cup in order to maximize daily revenue? And how many cups will be sold? And what will be the resulting daily revenue? Well, the solution to this is actually kind of interesting. Let's think about the number of times we reduce the price by 5 cents. The reason for doing that is because we're given information in terms of what happens each time you lower the price by 5 cents. So first of all, let's think about what happens to the price for each value of n. If n is the number of 5-cent price reductions, then the selling price will be $2.40 minus 0.05 times however many times you've lowered the price by 0.05. And then what else are we told? We're told that each time you lower the price by 5 cents, 50 more cups of coffee will be sold. So we're told that 50 more cups of coffee per day will be sold each time that you lower the price by 5 cents. So if you initially were selling 1,600 cups of coffee a day and you sell 50 more each time you lower the price, then the new demand, the new number of coffee that you sell each day will be that number. So what is the revenue? We see the revenue is a function of n, and it's given by this expression. Now, I can multiply all that out and get this is in factored form. Let's get a standard form. So there is a revenue function. Now the question is, how much should the coffee shop charge per cup in order to maximize daily revenue, and how many cups will be sold? Well, the key to both of those is to figure out how many times they should lower the price. That is, find the value of n that maximizes the revenue. We'll do that on the next page. So the conclusion is that to maximize revenue, the company should lower the price by a nickel 8 times. But the question was not to find the value of n. The question was, how much should the coffee shop charge per cup, and how many cups will be sold? Well, for that, we'll use these equations. The selling price will be given by this equation, and the number of cups sold will be given by this equation. So the selling price should be $2 per cup, so lower the price per cup quite a bit. The demand, the number of cups of coffee sold per day, will go up to 2,000. And then the last part of the question is, what will be the resulting revenue? The resulting revenue will be $4,000 per day. Let's compare that to the initial situation. The initial revenue, selling coffee for $2.40 per cup, selling 1,600 cups per day, the revenue is $3,840 per day. So based on the market survey, the coffee shop should lower the price to $2 per cup, sell more cups of coffee, a lot more, and increase the revenue to $4,000 per day. That's the end of that example. But I want to discuss what the textbook does for a similar kind of problem. They use the variable x as the number of 5-cent price reductions. So in other words, the price is given by that formula. Instead of $2.40 minus 0.05 n, they have $2.40 minus 0.05 x. And then the demand would be, instead of 1600 plus 50 n, it's 1600 plus 50 x. So then the revenue, that is the demand times price, is given by this expression. So they end up with a formula that has x as the variable, which is nice. It's nice to have x as a variable. But it's confusing because we no longer have this very familiar form. The revenue is normally x times p. In their solution, the revenue is this weird expression times this weird expression. X is not the revenue. In my solution, X was the revenue. X involved the value of n, but X still stood for the revenue. So I like n for the variable for this problem. It's the number of price reductions. But if you read the book, you might be a little confused because their approach is a little bit different.